Okay, so yesterday in class we talked about how we didn't have time for all of 8.4. Where I fell short was the error bounds. We talked about error in general, but we didn't necessarily talk very much about the error bounds or the formula you can use that will help you determine how you might minimize the error. So as part of that discussion, we have to recall that Taylor polynomials are an estimate, and with an estimate comes error, always. The moment you estimate something, the moment you introduce error into your problem. So that's a consideration with these Taylor polynomials. So with this, we need to kind of be aware of, get that back in place, be aware of how we can figure out what the error is without just guessing and checking, oh, what if I set this and see how much error there is? Because we can't always just do the straight up error like we did in class. So as a review, we need to recall that decreasing error or minimizing, to minimize error, we need to, one, we need to center appropriately. So that's your A value. And that can go a long way in making a good Taylor polynomial, just choosing the right A. And the other one that we can do is we can increase order, and that's your N. Okay? Put that down there. So to minimize error, we can center appropriately, and we can increase the order. These are the two ways that we can affect the Taylor polynomial to minimize the difference between the function and the Taylor polynomial. The goal being, truly, to make sure that our Taylor polynomial matches the actual function. We want to get it so that the f of x and the t of x are mapped onto one another as much as possible. And the difference, the area between those two spaces, that ends up being the error involved. So that's the goal, to get those two things so similar that they basically are constantly intersecting for whatever domain we're concerned with. Now, how close do we have to get? That depends on what we're doing, the tolerance of the project. And that might be any number of things depending on what you're working on. And as a scientist, as a researcher, as someone creating a model, you're going to go ahead and decide what that error bound is, where I cannot tolerate any more error or less error. And then you're going to use that to kind of work backwards and be like, all right, I need error of 10 to the fourth. So I need to have it less than 10 to the negative 4, excuse me. I need it smaller than 10 to the negative fourth. So then you will work backwards to figure out, well, how far out does my Taylor polynomial need to go to get that error that small? Okay, so in doing that, I have to give you your error bound formula, and that is Tn of x minus f of x, absolute value of, that has to be less than or equal to k, x minus a, n plus 1 over n plus 1 factorial, where k is greater than or equal to, so it's a maximum of fn plus 1 to the u. And u is between a and x, or x and a, depending on how your center and your chosen x value are located. So these values, let's kind of bear down on when some of these are. This part right here, this is the error, like raw error. The difference between the two functions is the same thing we used in class. So that error has to be the total error has to be less than or equal to this function. Okay? And the goal is to make this function approximately equal to some value that is less than or equal to the error bound. And that error bound is the max error that we can have. Okay, so if we decide, oh, I cannot have any more error than 10 to the negative fifth, that's my error bound. And I'm going to work backwards to figure out the other values. Now, n is what we're trying to figure out, that n value. That's our goal generally. Or you could use this to figure out a too, I suppose. But really, we're assuming that we've centered it appropriately, because that's a pretty easy thing to gauge just by eye, really. You know, oh, that a didn't work. What happens if I center it differently? Okay. So, you know, we've maximized the centering part. We want to figure out how far out does my polynomial need to go to make this thing work. So we're trying to solve for n. A is baked into the cake. X is baked into the cake because we're concerned about a specific value. N is the part that we need. What the heck is k? Well, k is a maximum value. See how k is greater than or equal to? So k, let me highlight, k, which is right there again, is a max value of this n plus 1 derivative. This n plus 1 derivative. And u is just some value somewhere between a and x. So basically you have your center point, and this is your a, and then you have the x. That's our concern. So we have a model and we have the a. The u is just all the points between there. And what they're saying is that k has to be bigger than all the other points in between a to x. So that's the consideration. So what we have to do, because we don't know how high n is, we have to determine this n plus 1 as the theoretical. So what you're really looking at is like, what is going to be the max of all these derivatives as I go out? And what would be the maximum value in all of these cases between x and a? And if you have an asymptote, then it becomes infinity. But in all cases, you're going to have a solid max value, no matter how far out in these derivatives you get. So that, especially in these problems. So that's where that's going to come into play. All right, so now that I've kind of explained to you this formula, let's go ahead and employ it in a problem. To do that, since this first introduction ran long, I'm going to go ahead and do that in another slide, and I'll do one video per example problem, so 2 additional videos, 3 total.